So this is lecture 1, lecture 2, kind of combine them together because lecture 1 is kind of short. Just to go over some background information going forward in what we need to do calculation-wise, and then getting into some review of material. So here is a table of some prefixes and numbers that we're going to be looking at. The ones you need to focus on are going to be kilo, of course, centi, milli, micro. Occasionally we might see something with nano, and pico when we get into some periodic trends. We will talk about the picometer. So I don't expect you to necessarily memorize this whole table, but I thought it was a nice table to kind of look at. So when we start to do some calculations, when you learn calculations in chemistry, you probably learn more of a proportion way of doing some problems. I'm going to be using what we call dimensional analysis. This is what you mostly see in college level chemistry. And so this problem kind of demonstrates that. And you're going to see it again when we get into some mole calculations and stoichiometry as well. So I have an airplane flying at a speed of sound at a speed of Mach 1. If I have Mach 1.5, which is about 1.5 times the speed of sound, if the speed of sound is 1130 feet per second, what is the speed of the airplane in kilometers per hour flying at Mach 1.27? So I don't expect you to know the English units, but 12 inches is a foot, and 2.54 centimeters is equal to 1 inch. I would give you that if I gave you a problem like this. So again, don't worry yourself about that. I more want to understand, can you do a problem like this? So what I like you to do is to pause the video and then come back and see what my answer is. So here you could see I have written out how I set up the problem. Again, with dimensional analysis, what you're going to see are relationships next to each other. And essentially what happens is you put the unit that you're in on the bottom so that it cancels out. And from here, I then converted it from seconds to hours, and then I took the inches to centimeters and went all the way to a kilometer. So again, when we're doing dimensional analysis, all you have to do is multiply the top and divide by the bottom. For these types of problems, I want to see some setup for work. So if you want to use proportions, that's okay. But this is a much more streamlined way of doing it, and you don't have rounding issues. So your final answer should be 1.57 times 10 to the third kilometers per hour, 1570 kilometers per hour as normal notation. And I will talk about when to use scientific notation, when not to. So on the bottom of this page here, I have some things I just want to mention to you. Length, we're going to see a unit called an angstrom. 1 angstrom is equal to 10 to the negative 8th centimeters, which is the same as 0.1 nanometers, which is the same as 100 picometers. Only reason I'm pointing that out is we will talk about the atom, and an angstrom is one of the units we use for the atom. Volume. Remember, 1,000 milliliters is equal to a liter. Also note that it is 1,000 centimeters cubed is the other unit. Another one that seems to be popular or coming back in popularity is a cubic decimeter is the same as a liter. So if you see that, just keep that in mind going forward. And mass, we have 1,000 grams is equal to a kilogram. Again, kilogram is going to be your standard unit. It is equal to 2.2 pounds. So the English unit, again, I don't expect you to know these numbers or memorize them, but for some of the calculations, they might be useful. So that's why I'm giving them to you. All right, and then we have density, okay? So please remember density is grams per milliliter, or it could be grams per centimeter cubed, okay? Now, if you're using a volumetric or graduated cylinder, you would use the unit of milliliters. If you have a cubic centimeter, that means you are measuring it directly using a caliper of some kind or a micrometer or something like that. but it really doesn't matter. Please keep in mind that most substances in the solid form that, or in the liquid form that we are dealing with, are between 0.5 and 22 grams per milliliter is the density range. So if you do any calculations and you're not in that range, there is something wrong with your calculation. Okay, so a quick calculation here. A square piece of aluminum foil is 8 inches on a side. So again, this is inches on a side. It's found to weigh about 1.863 grams. What is the thickness of the foil in millimeters if the density is 2.7 and an inch is 2.54 centimeters? So I'm going to take, again, my density, since that's grams, and I'm going to take how many grams I have here to kind of find my volume. Okay, so I'm going to take 1.83 grams and multiply that by my, or divide it by my density. Okay, so that comes out to be about 0.60 centimeters cubed. Area I could easily find because I have 8 inches on a side. So I'm going to take those 8 inches and I could square it, but I want to get it in centimeters. So you're going to see in my notes here that I have converted it to centimeters. So again, since this is a square, I could just take the square of that and I get about 410 centimeters squared. Well, if I want to know the thickness, okay, if I have a cubed unit and a squared unit, essentially my thickness is going to be my volume divided by my area. Because if I take the cubed unit of centimeters cubed and divide it by the centimeters squared, I end up with centimeters, okay? So if I take my 0.690 centimeters cubed and divide it by 410 centimeters squared, I will get about 1.7 times 10 to the negative third centimeters. But please be careful, I want it in millimeters. Again, this is just to kind of get some practice with some conversions. So I have the centimeter. I know for every 1 centimeter I have 10 millimeters. And again, for something like this, you don't need to show your work. Instead, I'm just showing it for your notes, All right, and then this page here with temperature. What I want to mention is we will be talking about heat versus temperature. Again, that's a big concept that we kind of covered first year chemistry. But Fahrenheit, do realize that 32 degrees Fahrenheit is your freezing point. 212 Fahrenheit is going to be your boiling point. The distance between those two numbers is about 180. Water, of course, is 0 to 100 when we're talking degrees Celsius, so that is a difference of 100. So from Fahrenheit to Celsius, it's kind of a pain. So instead, we just deal with Celsius in chemistry. The other unit that you will be seeing, especially when we get to gases, is Kelvin. So remember, the magic number is 273 plus degrees Celsius will get you to Kelvin, or the opposite. So if I take the freezing point of water is 273, the boiling point is 273 Kelvin. And why this is so helpful is because it's the same amount of units between them. Really, for our intents and purposes, for most of the calculations we're looking at, we are going to be looking at a change in temperature, so what we call a delta T. So it really doesn't matter, it doesn't mean you should really have to spend the time converting it to Kelvin, because you're going to see the same change. Kelvin will be important for a couple different places where we will have to use it, so that's why I review it. All right, and then the next page, again, I put this in your summer packet. So Please note that significant figures are going to be something that you need to kind of get the practice over. So please go over Pacific and Atlantic side. Again, where do you start counting a number, and do some practice if you need to. But I'm not going to really spend any class time on that. So the one last thing I want to mention in this particular discussion is just some notation of things that we're going to be talking about. So matter can be broken down into two different categories: a mixture, or what we call a pure substance. So a mixture is going to be a solution, and it can also be heterogeneous. So a solution is more homogeneous. Meaning that it's the same throughout. Heterogeneous mixture could be, say, for instance, a bag of Skittles is heterogeneous. You have a bunch of different colors there. Most of the time we're dealing with solutions in this class. But we also have what we call pure substances, and that's going to be kind of a vocabulary term that you might hear. So that could be elements, and most of you probably say, oh, I have magnesium, I have a piece of copper. That's a pure substance, that's just copper. But also, if I have something like sodium chloride, if it is just sodium chloride, that is a pure substance as well, if it's not with something else. So that's why I have that kind of noted on the bottom